Hello and welcome back to another mission tutorial. So this time we're going to work with this geometry. This is the Cessna 210, okay? This is an actual aircraft. We know all the performance, weight and so on. So this is another way to validate. You know the weight, you know how much lift you need to generate. Also, you know the drag of the aircraft, so you know how much thrust you must generate and so on. So fantastic case. The geometry was generated using OpenBSP. Okay, so it's a fantastic tool. So here you have the website, the link, also in the video description you will find it. Here in OpenBSP, you can find all the BSP version. Here you can browse and look for many geometries. The geometry that I'm using was an old one, okay, so I have it in an old OpenBSP format, in format 2.4, something like that. I need to convert it to the latest one, but in any case, I'm sharing the STL file. So as usual, we're going to work in the geometry, we're going to do the meshing. Also, we're going to launch a few simulations and to do a small study in performance. There is a lot to cover in this case, and in this series of videos I'm going to address only the basic meshing, and then I will dedicate another CFD cookie just to study performance and so on, because it's a very interesting case. As you can guess, we're going to put the propeller in motion and we're going to do a lot of stuff. So to show you what we're going to expect from this simulation, okay, at the very end, so here this is what you have. Okay, so we start from generating the meshing, okay, nothing is moving, doing some basic steady simulations to the sliding meshes and everything in between that you have the MRF approach. What you see here in this crease is the actual, no, this is a real deal, the sliding meshes, but also it is a less model. Okay, so it's not that expensive, okay, but yeah, you need to wait a long time, you need to iterate a lot, but fantastic case. And in case you're wondering, because always you have this, you're generating, you see the wake and the string tube and so on, is it generating thrust? And this is what I've been telling about the validation. There is not only looking at, like in other turbulence videos that we have seen, that we look at the theoretical values, also you can look at the physics, and here you can see that actually we're generating the thrust. Okay, so here we have the momentum, the excess, we're generating momentum, and we're going to see that also by changing the pitch angle of the propeller. So we're going to do kind of a parametric study because we have different geometry, so we're going to work with the script and so on. You're going to see from some situations to the others, you're going, in some cases you generate thrust, and in other cases you have the momentum surface, you are not generating anything. So it's up to you to pick up the best operating conditions. Okay, so to show you also the geometry, because there is a lot, I mentioned, and let me stress this, there is a lot to cover. So the geometry is coming from OpenBSP. So here you see I opened the version. This is as I mentioned, the old version 2.3. The latest one is 3.4. Use that one. This case now I'm using because this geometry was in that old format, and well, I need to convert it. But look at that. This is what we have. The first thing that we're going to see here, that this geometry, this is a very, very dirty geometry, okay? And in the sense that there are no intersections. So you are going to work, I'm going to give you the files already intersected, but I'm going to show you a lot of stuff, because in OpenFOAM there are some surface manipulations tools that you can find this intersection, or at least the edges that are intersected. But we're going to see also that you can do it in PowerView, which is fantastic, but also you can use on other applications like Fusion 3D, Professional CAD. You can do it also in Mesh Mixer. To some extension, you can do it also in Onshape. Probably you guys that I love Onshape. I'm not doing any publicity, but the guys from Onshape are doing a great job. But here, mainly when you take STL files that we're going to get from OpenBSP, you take it as a reference, so you need to do a lot of reverse engineering, so it can be a little bit time consuming. But in any case, what I was mentioning, that parametric study, so we're going to do these intersections, okay? And to mention something that many people know, including myself, I criticize a lot, Snappy Xmesh, but honestly it's a very good meshing up to the boundary layer step that we have seen that you can generate your boundary layers. But what I love about Snappy Xmesh is that it works really well with dirty geometries. This kind of geometry now where you don't have these intersections and so on, and multiple bodies, holes, okay, and much more. And comparing this with some other tools, for instance, fluent meshing that they have the tool for dirty geometries, also the tools that comes with Star CCN or any other mesher. I think Snappy Xmesh is at the same level. Okay, the only deficiency will be the meshing, but we can deal with that, and we're going to see that in this case we can generate with no problem. Okay, as boundary meshing. Okay, very easily. Okay, so the last part I want to show you about the geometry, that is very important. I always say you need to master your geometry. You need to own your geometry. Okay, and I don't need to explain why, okay, but just to show you, the importance of owning the geometry. In this case, let me go here, and by owning my geometry, I can simply change here, okay, this angle that corresponds to the right pitch, and I can do my parametrical study, my optimization study, whatever I want to do, okay. So the importance of owning their geometry, and also for meshing, defeaturing, removing details, and so on. It's very important to own your geometry. Okay, so at this point, this is only the introduction. I stress this one, there's a lot to cover. And to show you now before moving into the cases, but we're going to split the results. So basically, we're going to read this geometry here. In ParaView, you have the geometry, okay, the STL, I'm giving it to you, but we have different STL files. So each color here corresponds to a different STL. Remember, we need to intersect that or somehow compute this intersection, this line, to capture those edges. We know that we need to do that in a Snappy Xmesh. But also, okay, so we have this one, but we can have the simple geometry here. And look at that, I have only the body. This is the one that I will heavily use. Just for the one case, I will use another one. But this is the one that I will heavily use. And this one, I already intersected everything. I'm not going into too much details about that because, as I mentioned, that will be part of another video, okay? But this is already, the geometry coming out of the box from OpenBSP, and then using some other tool, I intersect everything. But then we can, okay, link this with a propeller. So we have here the propeller at high pitch, or okay, 0. So in this case, when we run, we're going to see that probably will generate thrust, probably not. So that's part of the study we're going to conduct. But then we can just simply substitute it and then put it in this position, which is feather position. In this case, absolutely is not going to generate thrust, or probably yes, who knows, but it's not the most efficient. And then you have some other intermediate positions, okay? So owning the geometry, the importance. And then just to show you here one mesh. So this is a mesh, okay? I didn't push the parameters. Well, remember, you just use finer surface refinement, you can get something much better. But this is very good mesh, okay? So look at that. We have here the refinement region. In this case, we added another region around the propeller. We're already thinking that this stuff is going to start to rotate, so we can create the region there. Look at that, you have the boundary layer. So it's not a super fine boundary inflation layer, but just to show that, and I can, with no problem, we can do something much finer. This surface refinement is not top, it's not the best of the world, so see that you have some problems here, but as we have been seeing on previous tutorial, this is related just surface refinement, so just finer mesh and problem solve. As most of the thing when doing meshing, use finer elements. And interesting also to show you, let me hide here and let me go and put, I think I have access to, let me see if I have access to that, and then okay, let me go here, apply probably. Okay, so I think I have information on the boundary layer. I'm not sure if it's okay. Yes, yeah. So surface layer, and let me put surface layers also in the propeller, and see that this is not that bad, okay? It's a very good cover as expected. In the intersections, we have some some problems, but everything just related now to the surface meshing. But pretty much you can say that this is 100% coverage here. Also pay attention that the geometry is not a perfect geometry. Okay, so we can smooth that geometry. And to show you here, look at that. The original geometry is kind of triangulation, a very vast triangulation. So you are also carrying on those defects to your meshing. But there are some techniques also I'm going to show you how to do smoothing. Okay, so finally, talking about now the simulations that we are going to run, okay, and to show you some results. So this is a case that we run, okay, we pre-compute this, and what we see here is that you have all the forces. So you have the lift, the drag, and then the side force. This is only the body, okay, and when I talk about the body, okay, it is only the fuselage, and then we compute the contribution of the propeller, okay? So the contribution of the propeller will be this one, okay? So, and look at here that what we're doing is changing the RPM of the propeller. So these steps that you see here, different RPM. So what I was telling now at the beginning, a way to validate or to look that we're solving the right physics. First, let's look at the lift. So this aircraft weight about 2,100 kilos. So here we have this this lift, which clearly is not enough to to keep the airplane alive, but important to mention that this simulation are run at half the cruise velocity. So if I double the velocity, I will quadruple the force. So kind of you start to see that this will fit with this 21,000 newtons. So there is no problem. Here you have a way to validate. But what is interesting here, you have drag force in the body, and look at that. Let's say that is something about, let's say 450, let's take the average, and we have that one. But if we look at the force generated by the propeller, so when we have negative force means that we're generating thrust, positive, okay, you are contributing to the overall drag. Look at that. For these RPM values, I don't recall, but I'm scaling from like 1500 to 2700. Look at that, you are not generating thrust, and then here you reach this moment that you start to generate thrust, but still it's not the same as the whole thrust force of the fuselage. So you are deaccelerating, then you enter into balance in something about here. So this here in this case, thrust equal to the drag. So you are in an accelerated fly. Okay, you are in balance, and then as you keep increasing, you are going to accelerate. And if you look at this plot, kind of you can get an idea. You can implement from this and PID control whatever you want. Okay, so this is also we're going to cover. Again, the stress a lot. There is a lot. Beautiful case. I love it. So stay tuned, and I'm quite sure that you are going to enjoy it, and I'm quite sure that there are going to be a lot of videos. In the folder that you are going to receive also, you are going to have different cases. So self-explanatory here is just one single body, nothing is moving. Okay, no zones here. We're adding the multiple reference zone. Here's the NCC, sliding meshes. This is the real deal. And this is the case that I'm going to show you first now to how to set up everything to demystify SnappyX Mesh, because you might be a little bit scared. Oh, but this stuff is going to be super difficult. No, you're going to see in this simple case, everything now is very easy, as we have seen so far. Here you have this folder that you have some document, because this is also a validation case. There is some data, so you can open there and find very interesting documents. The most interesting one is this one, because this airplane was used by NASA to conduct some experiments with natural laminar winds and so on. So here you have a lot of data, performance, coefficients, and so on. So it's a very interesting document. It's actual size. Okay, this is not wind tunnel scale, so you put it in the wind tunnel. So fantastic case. To stress something that what is reported here is using a natural laminar airfoil in the wind design. The geometry that I'm going to share we are not using that natural laminar airflow, but lift shouldn't change. Drag for sure is going to change, but pretty much that's not a big of a deal. So there you have some documents, and in geometry you're going to have all the geometries, and also you have some reference here, dimensions and so on, but you can find all that data in the internet. So yeah, that's all for this small introduction, and I'm quite sure that we're going to have a blast here. So as usual, give a like if you enjoyed this, okay, or subscribe, and I hope to see you in the next videos. Bye.